Hey everybody, it's Ripley back again. You guys are having a good day? We're going to talk about something called separable differential equations. And these are pretty cool because they give us an analytical way to solve for solutions of differential equations. The most important thing that you absolutely have to get out of this, it's kind of strange that I'm giving you something that has nothing to do with separable differential equations, but you need to understand that not all diff EQs, that's a Q by the way, are separable. All right, I think that's an A, isn't it? Separable? Yeah, it is an A. Sorry about that. Separable. That's important. So this is not a one-size-fits-all tool. All right, it's only going to work under certain circumstances, but you're going to get informed pretty quickly in terms of whether or not a differential equation is separable. Let me give you an example of a differential equation. How about let's do dy over dx is equal to, just for giggles, let's do y over x. Right, look at it. First things first, what do you notice? Is it a differential equation? It's an equation, check. Does it have an unknown function? Check. Does it have at least one derivative of that? Yeah, we're in good shape. Okay, now watch how this works. This is really simple. I'm just going to show you the mechanics of it first. Check it out. What I'm going to do is I'm going to separate the variables. So I'm going to put the x's with the dx and the y's with the dy's. And we'll get into this a little bit more closely here in just a second, but watch. What I'm going to end up with is dy over y. There are some techniques that we need to observe. Equals dx over x. Now what do you notice? What's begging to happen? Algebra tells us that in an equation we can do whatever we want as long as we do it to both sides of the equation, right? Everybody noticed what I did there, right? I stuck the dx over on the other side because this is an algebra, the Leibniz notation is an algebraic construct. I can break it up into dy's and dx's. Well, once you've got the y's with the dy's and the x's with the dx's, look at what happens. Booyah, I can integrate. Why would I want to integrate? Well, because then I can solve for a y, not in terms of some weird dx over y or dy over dx or something like that, but y as a function of x. True? Now watch, here we go. The antiderivative of dy over y is the natural log of the absolute value of y, right? And that equals, you know what? I'm not going to cut corners just yet. I'm going to call this plus c. Call that plus c1. And that equals the natural log of the absolute value of x plus c2, right? Everybody agrees. Now, for the sake of simplicity, what I'm going to do is I'm going to turn this into the natural log of the absolute value of y is equal to the natural log of the absolute value of x. Now, think about it. If I do c2 minus c1, don't I just get another c? The answer to that would be yes. Okay? Now, let's ponder this for just a second. Is y by itself? Almost. Is there anything algebraically that I can do to get y by itself? Absolutely. How do I make ln go away? Well, I do an e to that. What I do to one side, I must do to the other. All right? Now let's see what this turns into. E to the natural log of the absolute value of y. Let's see, what is that? Now the problem is that we got to think about here is our domain, theoretically, for this, if we were to draw this slope field, our domain is going to be all reals, right? I can grab a negative y, or I can grab a negative value, I can grab a positive value. The problem is that natural logs don't work like that. And that's why if we're going to evaluate a natural log of y, we got to take the absolute value of it when we take that natural log. However, when I undo it, I get my original y back. Why? No pun intended. It's because y could be whatever it wanted over here, so y should be able to be negative over here as well. All right, now we can discuss that more in class if there's some confusion there, but watch what happens here. This turns into, I'm just going to leave this as y equals the natural log of absolute x plus c, which if you think about, this is equal to e to the natural log of the absolute value of x times e to the c, right? Everybody sees where that comes from, right? Because x to the a times x to the b, if the bases are common, this is equal to x to the a plus b. Simple algebraic rule of exponents, true? So this guy turns into this guy. Well, what is e to the c? It's just another constant, isn't it? So what this turns into is a, right? We got a times there. And what is e to the natural log of absolute x. Well, we should think that it's absolute x, but again, starting originally, we know that x can be everything but 0, right? We're not allowed to have x be 0 in this term. So the solution to this is ax. This is the solution to that. If you don't believe me, let me prove it to you. Do you agree that if I take dy over dx of this guy, let's just putz around for just a little bit, okay? Dy over dx is equal to a, correct? Well, do you also agree that with just a little bit of algebra, a is equal to y over x, which implies that this is equal to y over x? Isn't that crazy? Now, the problem is we don't know what a is. A could be 17, it could be 93, it could be anything. What we created, if you think about it, is simply a family of curves. The solution to this differential equation right here that we started with is the family of curves of lines that pass through the origin that have different slopes. Any one of those is going to be a solution to that differential equation. So until they give us an initial point, you guys remember initial points, right? Initial points way back from antiderivatives, an initial value, which is x naught, y naught, right? Well, until I have that, I'm dead. So let's say that we take exactly the same problem, dy over dx equals y over x. We know that y is equal to a over x. But we say that this thing passes through, let's go with initial point 1, 3. That's easy, isn't it? Just like we did before, right? That's an x, that's a y. Wherever you see an x, stick a 1. Wherever you see a y, stick a 3. Guess what a is? Well, 3 equals a times 1. So a equals 3, which implies that y equals 3x. Easy. Nothing to it. Let's do another one that doesn't have, does not have a initial point, an initial value to it. Let's change the notation. Y prime equals y squared sine of x. All right? Now, I don't like y primes. I don't like y primes in general, to be honest with you, but I don't like y primes specifically in differential equations. First things first, let's look at this, what it really is. It's an equation, yes. It has an unknown function, yes. It has its derivative, at least one of them. Yes, we're golden. We got a differential equation. Now, if we're going to check to see if it's if it's separable. The way that you check to see if it's separable is if I can split up the x's and the y's. But the first thing I'm going to do is I'm going to do dy over dx is equal to y squared sine of x. And the reason I do that is because now I have an algebraic construct for the derivative. This y prime doesn't do me any good, but this does. For those of you that mistrusted or didn't believe Leibniz's notation was useful, if you haven't up to this point, even with integration through substitution and all that good stuff, now's the time to go, aha, I get it. All right, so watch this. I think you'll like this. We have dy over y squared is equal to sine x dx. I should probably use an implies error here, right? Well, do I have all my y's with the dy's and all my x's with the dx? Yes. Guess what? I can take an antiderivative. Now, this is where it gets a little bit tricky, but there's really not a whole lot to it. Watch. The antiderivative of 1 over y squared. Let's see. Well, the derivative of 1 over x is negative 1 over y squared. So shouldn't this be negative 1 over, whoops, not negative 1 over y. This should be negative, what did I say? Not negative 1 over, it should be negative 1 over y, right? Is equal to negative cosine of x plus c. Notice, just for the sake of being efficient, I'm not going to do the c1 and the c2 anymore because I know that they combine over with the independent variable to be just a regular old c. Now, watch this. I'm going to deal with my constants first. And the reason I do that is because that c is going to absorb some of those weird constant things. Watch what happens. Do you guys agree that if this is true, then 1 over y is equal to the positive cosine, oops, not sine, cosine of x. Now, you could write minus c here, but if I divide or multiply by a negative, doesn't a c just still be a c? So I'm just going to go plus C1. C1 may be positive, it may be negative. I don't really care. In absence of an initial value, I can't solve for it. So I just stay efficient and just call it a new C. If 1 over y equals cos x plus C1, doesn't that imply that y equals 1 over cosine of x plus C1? It's easy. Give me a point, I'm golden. Now, wait, let's check. Let's check one more time. Just, I know you guys hate this, but let's check. Let's see. If y equals 1 over cos x plus some c, all right? Let's take a derivative of it. Let's figure out what dy over dx is, and let's make sure it's a solution. You know me. I could be lying to you. It wouldn't be the first time. I'm going to think of, I'm just kidding. This is cos x plus c1, and this is, whoops, to the negative 1, right? That's going to make it easier for me. So I'm going to get negative 1 times cosine of x plus c1 to the negative 2 times negative sine of x. Those negatives cancel, and I end up with sine of x times, over cosine of x plus c1 squared.